Hello everyone, my name is Kurenkov, and today I'm going to discuss the results of our work. The title is NFOMP, Neural Field for Optimal Motion Planning of Differential-drive Robots with Nonholonomic Constraints. Authors of this work include my supervisor Dmitry Tsetserukou and other students of our laboratory. We will start with problem statement, then we discuss the contribution, system overview, and after that I will talk about the methodology and experiments. And I will finish with a conclusion of future work. Let's start with problem statement. The autonomous last mile delivery market is one of the most developed markets among professional service robotics market. Many technical giants invest in this market and many solutions exist, such as Yandex, Amazon, and Starship. Scalable and robust navigation and localization methods are required for sustainable development of this market. For navigation, motion planning is the most important problem. Motion planning is responsible for building a sequence of collision-free robot positions that connect the start and goal points. Key problems of current solutions include such issues as getting stuck in obstacles, going off the track, edge trajectories, and others. As a result, robot autonomy is limited in the real-world scenarios. The goal of this work is to develop an algorithm for solving the optimal motion planning problem for non-circular differential-drive mobile robots with non-holonomic constraints. The motion planning algorithm must be computationally efficient and at the same time maintain the critical path properties such as smoothness and density. Let's move to background. There are three main groups of sampling-based planning methods. The first one is lattice-based planners, where are fast and low-dimensional environments. However, we produce edge trajectories. The second group of planners are random sampling-based methods, we guarantee probabilistic convergence in a high-dimensional environment. However, we have low convergence rate and also produce edge trajectories. The last group are optimization-based planners. We are flexible and produce smooth paths. However, we use sign distance function for collision loss, and this loss has low capability to handle long walls and small U-shaped obstacles. To overcome these issues, we developed a new method, and we have the following three main contributions in this work. The first one is a narrow field representation of collisions that is learned online during path planning. The second one is a trajectory optimization method for differential-drive robots with non-holonomic constraints with the use of Lagrange multipliers. The third one is an optimization-based algorithm for optimal path planning of planar non-circular differential-drive robots. Let's move to our system overview. In this slide, the structure on NFOMP is presented. NFOMP consists of two parts, the obstacle neural field model and trajectory optimizer. The NF model predicts collisions based on input position. At the same time, the trajectory optimizer minimizes path lengths and finds feasible solutions. NF model training and trajectory optimization are performed simultaneously. For example, on this slide, you can see how NFOMP evolves over time on the warehouse map. Neural field after 10 iterations, 100 iterations, and 200 iterations and final trajectory are presented. Let's discuss the methodology of this work. Trajectory optimization of our method is based on the CHOMP algorithm. This algorithm represents the trajectory as a set of positions and optimizes the sum of squared first and second order differences. However, in our work, we represent the position as an element of C2 group by adding direction to our state. We use an obstacle model which predicts the probability of collision in the given position. We represent this obstacle model with narrow field. This model can produce gradients that push trajectory to feasible regions. One of the problems with CHOMP type optimizer is usage of sign distance function. This SDF leads to trajectory shortcutting and problems with long thin walls and small U-shaped obstacles. For U-shaped and uneven obstacles, directions of gradient of SDF collision loss function are perpendicular to obstacles, and they can even head in the opposite direction from feasible paths, which can cause a resulting trajectory to get stuck at this local extremum. To enforce non-holonomic constraints, we use Lagrange multipliers that are multiplied by constraint deltas that should be zero and maximized during optimization. The final loss function consists of three parts: the collision loss function, which pushes trajectory apart from collisions, the placing regularization, which minimizes a path length and smoothness of trajectory, and constraint loss, which forces position to non-holonomic constraints. For collision model optimization, we use the output of the narrow field with the sigmoid activation function. Gradients of the trajectory loss function are preconditioned based on the inverse pseudo-Hessian. Let's move to experiments. They compare NFOMP and GPMP2 in simple scenarios. The result shows that GPMP2 produces long paths for small wall and shortcut path when the wall is long. Moreover, GPMP2 gets stuck in a local minimum for small U-shaped obstacles. In contrast, our method can overcome these problems. On this slide, you can see qualitative analysis of our planner. These scenarios represent parking environments. I would like to note that our planner produces more efficient trajectories. Also, we show results on artificial corridor and forest scenarios. Also, we show results on the moving IE scenarios with model town environments. Here you can also see that our planner produces smooth and optimal trajectories. We conducted quantitative analysis and show that our planner superior classical solutions and GPMP2 in terms of smoothness and path length. We used benchmark framework that has predefined planners, environments, and metrics. On this slide, results from moving IE scenarios are presented. Also on this slide, results from parking dataset is presented. Let's move to conclusion. In our algorithm for solving the optimal motion planning problem in clustered environment is presented. Our algorithm is significantly superior to the most state-of-the-art approaches, outperforming them by 25% on normalized curvature and by 75% on the number of cusps in the moving environment. One of the disadvantages of proposed method is a relative large computation time. Let's finish with discussion on future work. We are going to increase the performance of the planner by using the modern JAX frameworks. Also, we are going to extend our planner to dynamic and high-dimensional environments. If you have any questions, I'm glad to answer them.